All right, so on Friday we talked about the basic concepts of loudspeaker directivity, right? So how these things work and why they don't necessarily spray sound evenly in all directions. And that's neither good nor bad, it's just a thing, right? So the loudspeakers just do that. They put more sound in some places and less sound in other places. Some important concepts I hope that you took away from that is this notion of a 6 dB down point. That, a lot of loudspeakers get spec'd in 6 dB down points. So when you look up a spec sheet and it says, oh, this is a loudspeaker that is 90 degree horizontal by 40 degree vertical, that doesn't mean that the sound just stops at 90 degrees. It just means that at a 90 degree beam width, it's within 6 dB. Okay? Once you get outside of that 90, it's more than 6 dB different from on axis. And more specifically, as we discussed on Friday, that it's not just that it gets quieter, it's that the frequency response changes at that 6 dB down point. Because not all the frequencies get quieter at the same rate. And so another way of thinking about it is that within that 6 dB range, whatever that beam width is that they give you, you'll have slight variations of level and slight variations of frequency response, but within that beam width, those variations are minimal enough that you don't have to be too worried about them. But once you get past that 6 dB down point on any axis, then your frequency response and or your level has changed dramatically enough that you have to be worried about it. Okay, that's the rule of thumb. Okay, so keep that in mind as we go through this. So what I'm going to do is take you through two examples today, two exercises for sort of plotting a loudspeaker in a space, figuring out where the sound's going to go. I just emailed all of you a little project I want you to work on this week. We'll review it on Friday, but I basically want you to do on your own what I'm about to do here, but for a different space. And I'll also send you some example loudspeakers if you want. But so we're going to use primarily polar plots to do this. So for example, I just have a little folder full of ones that I've found on the internet here and there. This is a spec sheet for a loudspeaker that Electro Voice makes. They call this when they say horizontal coverage is 60 degrees, vertical coverage is 60 degrees. So that's 6 dB down points. You go 30 degrees off axis in any direction of this thing, and you will go down 6 dB. But as we know, that's not the same for every frequency. So here's your different plots that we talked about. Here's your frequency response off axis curves. You can see beam width plot here. And you can see it really doesn't start getting directional until about 1 kilohertz. Okay, that's important to know. Most loudspeakers are not going to be particularly directional below 1 kilohertz. It's at 1 kilohertz they start being able to be directional. That's just because of the function of the size of things we tend to use. Okay, certainly if you get them larger somehow, you might be able to get them lower. But here's some polar plots. Now what's interesting about these polar plots is they're plotting multiple frequencies on top of each other. This is just to save paper, presumably. So if we look at this vertical one, for example, we have the blue solid line is 200 hertz, and you get 400, 800, and 1,000 hertz. 1,000 being the dashed orange line. Okay, so you just have to sometimes pay really close attention to these to make sure you're looking at the right frequency if they're doing this to kind of save some space. Okay, so I've got Stevens Center here, the section, and I'm going to take you through what would be involved in trying to figure out if this particular loudspeaker would work for this space. Okay, for purposes of this exercise, we're going to pretend the balcony is not there, or we just don't care about it right now. We're only going to try to solve the orchestra section. Okay, so the first thing we have to figure out is sort of where can we hang a loudspeaker? Where is it even possible for us to hang? We know that there's some space up here inside that eyebrow, but there's stuff already there. So we're assuming that we're going to, for purposes of this discussion, just bring something in temporarily for a show. And we're probably not going to hang it up in the eyebrow because there's already stuff up there. That's a pain in the butt. So we're probably going to hang underneath here. And there's a couple of rigging points here. There's actually a little point here where I've drawn this little yellow box. This is about where a box truss can hang. There's some points there that you can put one in, and you can usually hang off of there. So what I'm going to do is I'm just going to drop a little point there, and that'll be kind of the spot where I think I can put a loudspeaker. Okay. Now, of course, if this spot doesn't work, then I'll find some other things. The other thing I need to figure out is, what is the area where I'm going to be covering? If I'm not going to worry about the balcony for now, but we kind of want to set up the edges here. So just looking at the section view, the back of the back row is here, right? So I'm going to drop another point right there. And we usually want to figure this out where the ears will be, okay? Because the ears are higher than the floor, okay? And height matters in sound, right? Distance matters in sound. We've learned that. So what I'm going to do is just kind of move this. How high do you think the ears are? Yeah, it's somewhere between 3 and 4 feet. It kind of depends on the person and everything, but I usually just do kind of 3.5 feet just to keep things about average. So, so I'm just going to plot a little point 3.5 feet off the floor at the back row, okay? And then I'm going to go over here to the front row and drop a point there as well. Okay, so the front row, the ears would be around here towards the back of that front row, right? So I'll just take this, plot this at 3.5 feet. There we are. So what I'd like to see here is what is sort of the range of space that I'm trying to cover here. If I just draw some lines between where my loudspeaker is going to be. Let me turn on my object snaps here. Snap to node, thank you. And I'll do one right here. Okay, so what is this angle? Let's just see. What is this range? It's about 48 degrees, 50 degrees or so. Okay, so if we look at this this particular loudspeaker and we look at the spec sheet for it, we will see that on the vertical it's 60 degrees coverage, which is certainly large enough to cover this area I'm trying to hit, right? So it's not unreasonable to spend some time seeing if this would work. So that's kind of the first thing I always want to do, is just kind of look at what does the spec sheet say, what's the area I'm trying to cover, is this even a worthwhile exercise to see if this is going to work. And it looks like it will. If it really is 60 degrees beam width for the down points, and I'm looking to cover about a 50 degree area, then yeah, that's worth trying. Okay, so what I need to decide now is where should I aim this thing? So if I've got a 60 degree beam width and a 50 degree or so area I'm covering, where might you think I should aim this thing? That sounds reasonable. Well, yeah, so maybe like here, maybe? Because why would you say that? Okay, so well, let's figure out, using that logic, let's see what where would 60 degrees be? Because I don't want to overshoot it here. So, you know, if I just look at, you know, the stage, let's say the pit is raised, okay, for our show. Just to, if I just say, well, there's the pit, right? So now, if I want to try to keep it off the pit, what's my range now? 63. So, so even if I, you know, even if I put it by, you know, using that idea, even if I aim it towards the middle, then that's, you know, I'll hit that 60 degrees before I get to the pit, right? So that's a reasonable assumption. Let's go ahead and try that and see what happens. Okay, so I'll just drop a little point here. Oops, stop. Let's try that and see what happens. So I'm going to put this here, 3.5 feet up. Oops, not 3.5 inches. 3.5 feet up. I'm really not catting very well today, am I? I'm still not used to doing this with a trackpad. Okay, 3.5 feet. There we go. Okay, so I'm going to draw another line to that point. Let's see how this works out. So what I'm going to do is I'm going to call this well, I'm going to call it 0 dB is what I'm going to call it. Because this is my on-axis point. Okay, this is where I'm going to point the loudspeaker. So, oh dear. Who created this style here? All right, so that's going to be my 0 dB. Okay, and what I want to find out is if it's 0 dB here, how loud then would it be at the back row, and how loud would it be at the front row? That's what I want to find out. And I'm going to do this at 1 kilohertz. I'll start at 1 kilohertz because that is, you know, the lowest frequency where the loudspeaker even begins to be directional. So I don't want to plot anything below that. So I'll start there, and then if I have time, I'll work my way up the scale and see where we get. But we'll stick to 1K for now. Okay, so now what I want to find out is if I'm pointing on axis to that point, and then I go up to the back row, I'm looking at a 13-degree angle. So let's take a look here at this polar plot and see what happens. So remember, the orange line, the light orange line is 1 kilohertz. And we're doing, I believe, what does it say, 6 dB per division. So where would 13 be at 1K? Well, 30's here, so 15 would be halfway there, right? So, you know, 13 would be a little bit around there. So it's right about there. It's actually pretty close to 6 dB down, right, at 1 kilohertz. Okay, so that means that I'm already looking at a -6 right there. I'm just going to take this and copy it over here so I can kind of make some notes like this. Okay, so I'm already at -6. Okay, but there's a distance thing involved here, right? Okay, because the sound is going to be quieter back here because it's a little bit further away. That would be safe to assume. So let's find out. Let's figure out how much quieter. So what would be the dB difference there, just as a function of distance? Simplest way to figure that out is if I just get the distance to this middle seat, which is, somebody write this down, 52 feet 9 inches. So 52.75 feet. And Let's see where the back row is, how far away that is. The back row is 76 feet 11 inches. We'll call that 77 feet. So what is, if you just plug those two distances into a inverse square law equation, so 20 times the log of that first distance divided by the other distance, I'll find out the dB difference. Okay, so what is the dB difference between those two distances? Somebody try that? Make sure you put that first value on top, because I want to know. Minus 3.28. So we'll call that minus 3 dB. All right, so that means that I'm 3 dB quieter there with no, before I've even accounted for directivity. Okay, so if I'm 3 dB just as a function of distance, and then I'm 6 dB down for directivity, it's a total of 9 dB down at that receipt. Okay? See what I did there? Okay, well, that's not ideal, but let's see. So that's not very encouraging. Let's see what's going on here at the front row. So, same exercise. Let's take a look at what angle we're dealing with here. Okay, it's 35 degrees, it says. So what's 35 degrees? Now we'll go down on this side, because there are zeros here, so 35 degrees down. There's 30 degrees, so 35 degrees somewhere around here. So it's not quite, it's a little more than halfway between the two divisions. So it's not a full 6 dB down. So it's probably closer to 4, I would say. 4 dB down. So there we get a minus 4 dB just as a result of directivity. But what about distance? It's closer here, so it's going to be louder potentially at the front row, because the front row is closer to that place, right? So this distance is 33 feet 7 inches, so call that 33.5 feet. So somebody tell me the dB loss or distance value between that original distance we measured for the middle row and the distance to the front row. Should be a positive number. $33.5 feet to the front row, and then somebody wrote down that middle row, right? So 52.75. So put that on top and put the 33.5 on the bottom. 3.9. So we'll call that 4 dB. Okay, so it's plus 4 dB because of distance, but minus 4 dB because of directivity, which means it's 0. Okay, so that cancels out. So in this case, the front row is going to be just as loud as the middle row for this frequency, but the back row is 9 dB quieter. Okay, that's not within the 6 dB range, right? That we would like to be in. So, do we understand what happened here? Why is the front row the exact same level as the middle row, even though it is at a different distance and it is off axis? So if it's closer, what happens? Less loss over distance, right? If it's closer, it'll be louder, because more distance equals quieter sound, okay? So we're louder because we're closer. But at the same time we're getting closer to the loudspeaker, we are also getting off axis of the loudspeaker, and therefore it's getting quieter at the source. So the source is getting quieter as we are simultaneously getting closer to it. And so it's theoretically getting louder because you're closer, it's also getting quieter because you're going off, and that ends up equaling out. So if we kind of took that observation, and instead of giving up on this loudspeaker quite yet, what if we could take that idea and see if we could, how far we could stretch that idea, right? So if we know that we can see that that balances out, as you get, if you can set it up so that you're getting closer to the loudspeaker at the same rate that you're losing by going off axis, can we keep that even all the way across? So what if we do what Will's been trying to get me to do for a little while here, is what if we just aim at the back row, okay? So if we aim at the back row and say, that would be my 0 dB now, and then I'm going to, our theory here is as we go towards the front row, we're getting closer to the loudspeaker, so it will be getting louder, but we'll also be going off axis, and therefore it'll be getting quieter. And can we get that maintained as much as possible? So if that's our 0, let's just forget the middle row exists for now. We'll just look at the range between the front and the back. So what is that new angle? Anybody remember what that was again? 48 degrees between the back row and the front row. Okay. So 48 degrees, there's 30. So 40, 50, it's right about there. It's like 6 or 7 dB down. Okay, so let's just say 6. So minus 6 dB to hit that angle. But what is the difference in distance? Remember, do you still have those two distances written down somewhere? Distance to the front row and distance to the back row. Can you tell me the dB difference between those? How much louder is the front row than the back row? 33.5 was the front row, right? So it's like 7.23 dB is the front row is that much louder, right? So against a minus 6, then we're really 1 dB, right? Okay. And depending on how you squint at this thing, you might even say that I'm minus 7 anyway. It's hard to tell because the dash straddles the line. I'm trying to see the intersection of it, but if you really kind of, you might say, oh, that's actually 7, and that would be closer to 0. But we know it's within a dB, and that's enough that no one can see. And again, the idea there is within that 6 dB down range, that's where theoretically the frequency response stays consistent enough that we're okay with it. So here now we've gone from a range of 9 dB between front row and back row to now a range of 1, maybe 0 dB between front row and back row, purely by changing the way we aim the loudspeaker. This is one of those tricks that will sort of instantly separate the professionals from the amateurs. Okay, is this idea of aiming the loudspeaker to the back row because of this idea. It almost always pays off to use that strategy. It's not unreasonable to say, well, to assume that I'm trying to cover this area, so I'm going to aim at the middle, and then I get the best of both worlds. But if you don't take into account that notion of difference of distance, then you realize that doesn't actually work. You end up with a vastly different level at the front row from the back row. So if you aim at the back row, the idea there is the back row is the farthest away, so you want that to be on axis. You don't want to be taking any extra loss at the back row by directivity because it's already the furthest away. So that's on axis. You want that to be as loud as you can possibly get it because it's the furthest away. And then as you get closer to the loudspeaker, you're also going off axis, and therefore it evens out. So that's just sort of a rule of thumb, generally speaking. Try aiming at the back row because you can balance out this notion of directivity. Cool, right? Right? We didn't have to spend any money at all to solve that 9 dB problem.
So, just to clarify, you're aiming the center of the speaker at the back row, and so that dispersion is actually 60 below and 60 above, not 30-30.
No, it's 30-30.
Okay. Well,
So we're looking at, I'm looking at 1K, But if you look at, this is where this loudspeaker kind of falls apart for this particular application, is if I go up to some higher frequencies, for example 2K, we'll see that at 2K at that same angle we're actually 12 dB down, right? So if you only look at one frequency, you might think that this loudspeaker would work, but in reality it gets a little bit too narrow at the higher frequencies. We could rerun that math and we'd see that. Now in reality we would still be within 6 dB, right? The front row would be still within a 6 dB range. So and it would be within that frequency response range where we could deal with it. So it might still be okay. But more importantly, so when they say 60 degrees, that's what they mean is 30 degrees to either side. And you can see that there's your 6 dB down point there, 6 dB down point there. That's a 60 degree thing. So this is the other thing you have to think about when aiming at the back row is that you know that the speaker's also spraying just as much sound on the other side of that axis. So in this case, I got a balcony there, so I don't care. But if I had not a balcony there and I had a ceiling there or something, then I'm shooting a lot of sound at the ceiling. You have to kind of think about that. Do I care about that? Is that something I want to worry about? I don't know, maybe. Depends on what the ceiling is and what angle it is. Is that going to cause you trouble? It might help you, actually. It just depends. Okay, so that's just a first kind of dipping our toe in the water here. Let me try now something a little bit, well, a lot more complicated. So let's see, where are we? Yeah. You can use anything that you can find a polar plot for. Okay. Anything that you can find a polar plot for. All right. So let's take a look here. This is DeMille. And we know that there is a loudspeaker center cluster that we leave hung up in there. Anyone know anything about that little cluster that we leave up there in DeMille? Anybody ever looked at it very closely? So it's called a KF300. Here is the data sheet on it. You can see horizontal, it says 90 degrees between 6 dB down points. Vertical is 50 degrees between 6 dB down points. So that's it in all its glory. So let's take a look here at, anybody know approximately where that sucker is hanging?
It's like right in front.
It's just barely in front of this proscenium, right?
Yeah.
It's like right here. So I'm just going to drop a point here. Somewhere. It's right about there. All right. Point style. There we go. Okay, so they said on horizontal it was what? 90 degrees, so 45 on either side, right? Okay, so let me just draw a line here and see where 45 degrees lands. I don't think, is that 0 really? So there's 45. Okay. Okay, so there's 45 degrees. So that is not all of the audience, right? But you might find that there's 2 of them hung up there, right? If you've ever looked very closely. Well, why is there 2? Well, because 1 doesn't quite cut it. Okay. So here's what is interesting about this. How is it? Remember, I've said that you put 2 loudspeakers right next to each other at a slightly different distance away from the audience, and they will do what? They'll comb filter like crazy, right? So how can we possibly have 2 of these KF300s sitting right next to each other, pointed, at the same audience, and have them not comb filtering like crazy?
I mean, they're kind of faced away from each other, but not really. But it's still comb filtering, isn't it? And you have a sub in the center of it, so they're a little farther away than that.
Well, that farther away would make it worse, make the comb filtering worse, right? Well, eventually it makes it better, or it sounds better to us. It is actually worse, but sounds better. But it would have to be at least like 5 feet away from each other and they're not that far away from each other. So, sure, yes. Yes, but why? So, yeah, remember what happens when, like, if in sound pressure level in the air, if you have 2 levels, right, 2 sound pressure levels that are the same, and you sum them together, and if they were perfectly in phase and time, then what happens to it, that level? It goes up 6 dB, right? So here is the theory behind what we're doing. If I took this 45-degree angle and let's see, what if I'm going to do reference. Okay. So there's my 45 degrees now. So it's like going all the way. This now is going to hit everything, right? Yeah, but we hit 6 dB down right in the center. But if I could get another one of these and point it the opposite direction, so it was pointing over here, and those two 6 dB down points were overlapping in the same spot, and if I could somehow get them to hit that spot in the center at the exact same time, all the way down that center area, if I could get it to hit the exact same time, and I'm talking exact same time,
Exact same time.
then I would get a 6 dB boost, wouldn't I? Right? And that point is the 6 dB down point of the loudspeaker. So the loudspeaker is 6 dB quieter at that spot, and if I can get 2 of them that are 6 dB quieter on axis to overlap at the exact same time, then I will get a 6 dB boost, and they will sound just like they were on axis of 1. Okay? It sounds impossible, but it is actually possible.
Because those edges are that clear.
Yeah.
On when they say.
Well, if it's a well-designed loudspeaker with a good horn, then yeah. The idea there is that, at that point where the 6 dB down is, if you can get that to be perfectly in time, you get that 6 dB boost, and then you move, a little bit to the left, a little bit to the right. One of them is getting louder, and one of them is getting quieter, and therefore they're not the same level. And same level is one of those variables that you have to have in order to have comb filtering. Same level, different time. Okay, but if you have different time and different level, then comb filtering is not that bad, right? So that's the idea here. So let's see what happens if I try to take this loudspeaker, and if I just point it. So how far off am I trying to point it here? It's really, what is the angle? It's really 45, right? So if I can aim it on axis to 45 degrees, like right there, then we could then plot this and figure out where we are. So we know that if we pull this off right, then get rid of this for a second here. So if I mirror this now, again, okay, so if one of these lines is the on-axis point for one of these loudspeakers, and this line is the on-axis point for the other loudspeaker, and if I'm confident that I can get them to overlap at the same time there, which I could, I would need some analysis equipment to do that. I would need a couple of analysis mics along that row, so where I could see the phase relationship, and I'd have to kind of really tweak those distances to get them to hit that spot at the same time. Then, in theory, everything between these two lines would behave like it was on axis. I've effectively created a single loudspeaker that is twice as wide of coverage. Okay, because everything in between these two on-axis points would behave as though it was on axis to one of them, because I'm leveraging that 6 dB down. Okay, so let's plot this now and see how it works. So let's see. Go ahead, just to keep things consistent, I'll figure out where this would be on the vertical. So here's my section. And I'm going to say that the loudspeaker will hit somewhere around there. Okay? And let's now let's figure this out at the section like we did before. So I'm going to plot my points again. So here's the back row. And how high off the ground do I want that? 3.5 feet-ish? No, 3.5 feet, not inches. Keep forgetting to scale this thing. 3.5 feet. There you go. And then the front row, they'll put assuming the pit is up, they'll actually put a row of seats right there at the edge of the pit. So the ears would be here. So my front row would be, do it again. .5 feet. Okay. And just for fun, let's put a point in the middle row so we can see how that would look. There we go. All right, so I got 3 points there. And just so I can make sure that I find the corresponding spot on the ground plan, I'm just going to draw some construction lines off of there. You know about construction lines, right? Yes? Okay. You are being taught CAD, I hope. Okay, there we go. All right, so the corresponding spots here then are there, and there, and looks like there. Okay? You with me so far? I'm just kind of lining, I've got 2 drawings here, I'm just lining up the spots so I'm going to make sure that I'm measuring the same place in both drawings. So let's figure out now, I'm going to aim at the back row, because I know that that's what professionals do. So I'm going to make a little note here of that this will be 0 dB. Hopefully larger. These TDs, and they're like bizarre. Come on, give me something better than that. 12 inches. What is going on? Get it bigger if I go somewhere else. Ooh, how about title? That sounds like it might be bigger. No. Foot. If I do that. Is that my problem? Ah. Dough. I'm gonna do it over here. There we go. Okay, so that's my 0. Because that's where I'm going to aim it, is on axis to back row. Well, I'm going to draw a line from the loudspeaker to the back row. So I have some sort of reference point. Ooh, I need... TDs also don't like nodes. Where are you? Okay, so it's there. And now what I want to find out is what level will I get at these other 2 spots. So there's a spot there. And there's a spot here. So what angle am I dealing with here? 13 degrees. Okay. So let's take a look here at our polar plot. Got one for everything. So here's vertical. So you can see it starts getting directional at 2K. Right? So let's yeah, let's do it at 4K because 4K looks pretty consistent. Okay? So we'll plot this thing at 4K. And I'm saying that I went, how many degrees did I say? 13 degrees. So 13 degrees is going to be right about there. And if this is 6 dB per division, which I believe it, yeah, okay, so here's our key, 6 dB. So yeah, it might be 1 or 2 dB. So we'll say, well, yeah, let's just say 2 just to keep the numbers round as possible. So I'm minus 2 dB. Now this is at 4K. And when you do this for real, you have to do it at more than one frequency just to get a good sense. Okay, what about distance? What's my difference in distance that I'm dealing with here? So we go, that is 31.5 feet as compared to 39 feet. What's the dB difference there? Whatever I said it was. I say it out loud so that I don't have to remember it. 1.85. So I'm going to get. So it's a 2 dB increase. Okay. So I'm just going to make a note here. Minus 2 dB for the angle, and plus 2 for distance. I'm just making a note because I'm going to need this information later. So that equals basically 0 dB. Okay, so the reason I'm not collapsing this is you'll see later I'm going to need to refer back to that. I don't have to do that math again. Okay, because I'm going to need that math again later. Okay, so what's this angle now to the front row? That is 41 degrees. So where's 41 degrees on my polar plot here? Well, there's 30. There's 60, so it's going to be kind of a third of the way, which should be about here. Hey, that's like the 6 dB down point. Ish, right? Right about there? You see that? Everybody understand how to read this thing? I'm looking at about 6 dB down. So, cool. We'll take this, and I'll copy this down here. So I am at -6 dB for the angle. Now, what about distance? Anybody remember what the distance to the back row was? Did you write that down? Distance to the front row is 22 feet. So 22 feet as compared to distance to the back row. What's our difference in level there? Anybody? Does anyone remember what the back row distance was? Do I need to do it again? 22 feet to the front row and 39 feet to the back row. Now write that down. This is a lot of data we got to keep track of. 5 dB difference. Okay, so it's +5 for distance for a grand total of -1 dB at the front row. It's pretty good so far, yeah? So far, so good. Okay, so what I'm going to do now is I am going to take that data that I got and I'm going to copy it up here to my ground plan view so that I have that information handy. Okay, so there's that one. And here's this one. Go there. I probably should have picked one row lower, shouldn't I? In the middle of it. That's all right. All right, I'll take this one. And that'll go there. Okay, so vertically this works. Let's talk about horizontal now. How do we figure out horizontal? Well, next thing I would want to do is plot some points at these same rows, but at this on-axis spot. Okay, so there's that one there and that one there. Now, I know that vertically I am on axis there. Or horizontally I'm on axis, right? If I've got two of these things and I'm going to splay them like this, horizontally I'm on axis at this point, but vertically I'm not exactly the same distance. If you actually look at these things together, because this curves, this seat is not necessarily the exact same distance away as this seat from the loudspeaker. You see what I mean by that? So how could we figure out exactly how far away it is? Because it's not the front row at that seat is not 15 feet 6 inches away. Do you understand why? Why? Somebody tell me why. Why is it? CAD just told me it's 15 feet 6 inches. So why is CAD lying to me? Yes, because there is a z-axis involved here, right?
Z-axis.
But this is not a 3D drawing. So how can I figure out where exactly that seat is and how far away it is in reality from the loudspeaker?
With triangles.
With triangles, yes, with triangles. Yes, there we go. So we're going to do a little bit of trigonometry here to figure this out. Okay, and you all took trigonometry, so you should know how to do this better than I do. But okay, so Pythagorean theorem is a squared plus b squared equals c squared. So we're going to call a this distance that I measured, which is 15.5 feet. So I'm going to write that down. A equals 15.5 feet. What is b? I don't know. Let's see. So I'm going to take a little tap off of this point here. And I'm just going to Draw a line there. Okay, so if I just get a dimension here from that spot to that spot, I should get B, right? And that's 17 feet 3 inches, so 17.25 feet is B. So give me the square root of A squared plus B squared. Anybody do that? You know how to do that? Okay, so I'll show you how to do this on pCalc. Okay, so what was A again? 15.5. And you should have a little button that says x to the square, x to the power of 2. So I'm going to hit that, and I get 240.25. I'm going to plop that number into my memory because I'm interested in that. And then what was B? 17.25. And I'm going to square that, and I'll add that into my memory. So now I'm sitting here at 537.8125. I'll bring that back in, and I will take the square root of that, and I get 23.19 feet. That is the actual distance that that seat is away, right? So somebody write that down, 23.19 feet. Anybody remember what the distance to the center front row was? Anybody wrote that down? So 22 feet, yep. So we're talking about the dB difference between 22 feet and 23 feet. What's the dB difference between 22 feet and 23 feet? It's not going to be a lot, but so half a dB. Certainly not much to get horribly worked up about. So let's just go ahead and make a note of that. Put this one over here. Oops. Back. Okay, so at distance, it's really we're not getting quite plus 5, right? We're getting 4.5. We're half a dB, a little bit further away. So now where does this land us for this seat? -6 compared to 4.5. It's really -1.5, right? So we're at -1.5 dB at that spot. Okay? See how this is going to work? Okay. What about this seat? Well, what is A for that seat? A is 31 feet 7 inches. So we could call that 31.5, I think. An inch is not going to kill us. All right? So 31.5 is A. What is B? Well, B for this row is different, right? Each row is a different height, right? In most theaters. Well, then nobody could see. Okay, so B is 12 foot 4 inches, so we'll say 12.3 feet. Okay, so how far away is that seat? Say that again. 33.82 feet. Okay, somebody write that down. As compared to what was the original distance for the center? Nobody wrote that down, so we'll do it again. 31.5, 31.5. Okay, so what's the dB difference between those two numbers? Anybody get it? Okay, so another half a dB, right? Okay, so we're really saying only plus 1.5 here, which is really going to have me at minus half a dB from one-axis. See how I did that? Everybody with me? Have I lost anybody? Please tell me if I've lost you. Okay. All right, so far so good. Within that area where we said we are more or less on axis, and because this is symmetrical, we could flip this to the other side and be the same. Right, the other side of the theater and be the same. So we only have to really solve one side of it, and we'll have the other side automatically. So far, we are within 1.5 dB at 4K. That's pretty good. Would you agree? I think so. All right, so let's see what is our next most extreme angle. So the next farthest spot here for this row would be there. That's like you go all the way to the edge. See how far off axis I can go there. And then for this other one, it's probably, what's the furthest that they could ever possibly want to put a seat? Maybe there. They're not going to squeeze anybody in right there, right? Because there's just not enough space to put a seat there. Yeah. So, but let's say that's as far as we're going to care. Okay. We're not going to worry about anybody who's sitting any further over there than that because there's no room to put anybody there. Okay. So. So I've got a new line that goes there, right? And another line that goes here. Okay. Now, at these two spots, we are both off-axis horizontally and we are off-axis vertically at the same time. Right? Because we are both to the side of the speaker, and we are a little bit below it. Understand? So we're getting hit twice at these seats. Okay? So let's figure out, we already know we're getting hit minus 2 dB because of the vertical. Okay, we already know that because that's what that row is. So if we're just looking at this seat here. What about the horizontal? Well, let's just look at this angle. That is 15 degrees. Okay, well this is a vertical polar plot. I want a horizontal polar plot, don't I? So let's go back here, see if we can find a horizontal polar plot for 4K. Hey, there it is. Okay, and I said I was how many degrees? Somebody write that down? 15? Okay, you guys are learning. Write it down. Okay. 15 degrees, I mean, I'm still, maybe I'm 1 dB down. Maybe, if I want to be super persnickety. Half a dB, we'll split different. So we're not that far off to be worried too much, okay? So we're, I'm going to modify this, so minus 2 dB vertical, minus 0.5 dB for the horizontal. What about distance? How far away am I? Well, let's see. A would be... Oh, wait a minute. Hang on. I changed the wrong thing. Hold for sound. I need to copy this data over to here. Right? Okay, so I'm minus 2 dB for vertical and minus 0.5 dB horizontal. Okay, now what about distance? A is 33 feet 7 inches. So we'll call that 33.5 feet is A. Remember what B was for that row? Write that down. middle one. It was 12.3 feet. That's B. Write that down. Okay, how far away is that C? Somebody? Bueller? Bueller?
35.686 feet.
Okay, I got one person that got that answer. I need 2 more people to get that answer before it's right.
They both look like they used his calculator. I can confirm you did the math.
Okay, then I need 1 more person before I will accept that answer. Oh my goodness. Guys, this is a lot of data to wrestle. You've got to write it all down. I'm going to ask you to do this all by yourself this week without me telling you to write down every bit of data that you measure.
I'm not going to be able to write it down.
I need one more person to get me, what was it, 33.5 feet?
No, it's 35.6.
35.68 feet.
Okay, I got it.
Okay, 35.68. All right, so that distance then compared to, so you can write that down, 35.68, right?
Yes.
Okay, so that distance compared to this distance, which was 31.5, what is the dB difference? Should be a little bit less, right? dB difference between those two distances. .08. Yes? Is that negative or positive? Because yeah, but was that, am I closer or am I further away? Further away, yeah. So I need to, for distance, I need to take off how much? Okay, so I'm really now at 0.5, right? Half a dB for distance. Okay, so that means total I am minus 2.5 plus a 0.5, which means now I'm at total of minus 2 at this seat. Yeah? Do we follow that traversal? Okay. Now, so this will be the worst case scenario, this seat. This seat is the furthest off axis horizontally and vertically, and it is the most difference in distance compared to back row center, right? So let's just see what we end up with there. I'll take my little values here. So the reason I'm like copying this is I don't want to have to refigure all this data again. Right? I'm just sort of, rather than going all the way back to square one and figuring it all over again, this is why you like write every step down, so that you can always go back and figure out, you know, where you have to intercept that data to introduce these new values. Okay, so I know I am minus 6 dB on the vertical. But I am also off axis horizontally here, aren't I? Yes, I am. So how much off axis horizontally am I? 31 degrees. 31 degrees. There it is. I might be 3 dB down there. If I'm overestimate a little bit. Yeah, somewhere between 2 and 3 dB, right? Because it's 6 dB per division. So let's just say minus 3, just so we're not trying to make this look rosier than it really is. I'd rather err on the side of being a little worse than better than I know for sure. Okay, so that means I am going to say minus 3 dB on the horizontal. Okay, so because of directivity alone, I am minus 9 dB total at this angle. Okay, now it's probably not quite minus 9 dB. I mean, because if you actually go and measure the sum of those two angles in real life, you know, it's not quite as big of a double whammy as that, but that's the only information we have, right? We only have 2 axes here, so we just have to put both of them in and know that it will be in real life a little bit better. That's the beauty of something like ease, is that ease has data for multiple axes, okay? But for now, we just have to work with the data we're given. The data we're given only gives us horizontal and vertical, so we'll just assume that they both happen at the same time, and we get a full 9 dB drop. But distance, we are quite a bit different here than back row center. So let's figure out this distance. A is, get ready to write this down, 19 feet. Anybody remember what B is for the front row?
17.25 feet.
Yes, finally! Somebody wrote it down and remembered it. Okay. So, all right, so those two distances, give me the actual distance now for that seat. Square root of A squared plus B squared.
25.66. Oh, that's 3.
Okay. Everybody else get that? 25.66? All right, so 25.66 as compared to, anybody remember what the distance to front row center was? Yep, 22. So what is the dB difference between 22 and 25.66 feet? It's going to be a little bit quieter. 1.34. Okay, so that means by distance, I can take 1.34 off of that plus 4.5, right? Because I'm a little bit further away. So that would be, let's just call it 1.5. Okay, just to make this a little bit easier, which would take me to 3 even, right? Plus 3 for distance. Okay, so what does that work out to then in the end? It's a minus 6, isn't it? Which is within the range that I can accept. Yes?
They weren't.
At 4K.
4K. Now let's do for 2K.
Yeah, so now you got to do it for probably 2K, 1K, and I would do at least, you know, and probably 500 just for good measure. Okay?
They also do have that sub.
Yeah, but the angle, we just keep, as long as we keep the angle the same, right? Because we know what the angle has to be now, right, to do this. As long as we keep that angle the same, even if we pull them apart, keep the angle the same, then they still sum together the same way. So that's okay. All right? So, your mission now, between now and Friday, is to do exactly what I just did, but for a different space than I've done. Now, for the undergrads, you're going to do Friedman. For grads, you're going to do Catawba. Okay? And so, for the undergrads, what you're going to do is you need to spec me a center loudspeaker or cluster of loudspeakers, if necessary, that will cover that whole seating area within a 6 dB range, okay? For, how many frequencies did I say? 4 frequencies. Okay, so which 4 frequencies do you think we ought to do?
501K.
There you go, okay? So you got to give me those 4 frequencies.
43.
and I want to see we're within a 6 dB range for the entire seating area. Okay, you cannot use the DBQ7 or the DBQ10 that we normally leave hung up there, because then you would just sort of copy with that and never have to actually think. So try to look some stuff up. Now, I can probably, if you want, I can email you all some polar plots that I have, but you could also go and look some others up if you'd like. Okay. So what I'm looking for is basically this kind of CAD file with all the different points, and I want you to, and you might have to, if you're doing more than a frequency, you may ultimately have to just break this out into a spreadsheet, right? And start labeling all these points. This is seat A, B, C, D, E, just so you can keep track of them all, and say at each frequency, here is the level with all the little, and I want to see all your work. I want to know, here was the angles, this was the loss for the distance. I want to see how you got there. Don't err on the side of giving me too much data, is what I'm saying. Okay? And I'm going to see it for all of our frequencies. And you have to do it, you have to plot 2 loudspeakers. Okay? I want 2 different options. Pretend that you are a consultant that is trying to tell me to buy something. And I want 2 options to choose from. And then you need to tell me, of the 2 that you chose, that you plotted, which one would you recommend based on the data. Okay? Yes?
Yeah, quick question. Well, this costs, like, the recording screen is cost,
Yes.
but I've noticed that none of the, like, did you get this semester?
Well, so I've been lazy about that because so far they're pretty similar to last year, so I've just been leaving them. But yeah, I can do this particular one. I can post that for sure. I'll do it right now. So grad students, what you guys are going to do is Kataba, but what is particularly challenging in your case is you've got to make it work in a 360-degree horizontal, but you've got to contain it on the vertical. Okay, because ideally we'd like to keep it off of as much of the stage as possible, but be able to hit those seating units no matter where we move them along the perimeter of the room. Okay, so you've got to come up with a center cluster that can spray the sound equally at every angle horizontally, but focused as tightly as possible on the seats on the vertical. That will be a little challenging. But I have to make you guys do harder things. Okay. Any questions? Other questions about this?
Yeah.
Are you gonna look at our lesser if you've chosen to do some crazy like 5-part center cluster?
So
Just so we don't shoot ourselves in the foot by like doing something too funky.
well, keep in mind that in order for like an array to work, you have to have what's called constant directivity. So let me show you what I mean by that. That's probably down here.
See, I don't want to get on this project.
Okay, here we go. So here is a beam width plot for this loudspeaker. You see how we have, for the horizontal, pretty constant directivity. I mean, we're not a whole lot of deviation from 1K above. Lots of deviation below 1K. On the vertical, it's a little bit more deviation, but still, not as dramatic as. All right, so you need something. You're looking for something that has a pretty consistent beam width for, around 1K and above. So that's the only way that splay at the 6 dB down angle. That's the only way that works. Is if all the frequencies that are small enough to comb filter, those have to be decaying at the same rate. Because if they're all decaying at a different rate, then they're not all going to hit the 6 dB down point of the overlap, right? Because these aren't, these low frequencies aren't going to hit at 6 dB down, even though the high ones are. So why do we not care about that?
They're not.
Yeah, you can't. But if you're going to splay, if you're going to create a cluster like we did, those are going to overlap not at 6 dB down. They're going to overlap at 3 or 2 dB down, or maybe no dB down. And what will happen to them? Maybe they'll cone filter, but how much out of time or phase would they have to be in order to cone filter, in order to cancel out? You know, it takes 180 degrees, right, to make a difference. It takes at least 120 degrees to make a difference at all, right? Well, no, but think about it. Like, how big are those frequencies? Their wavelengths are pretty large. So, you know, at 100 hertz, for example, that's a 10-foot wavelength, which means you've got to be at least 4 feet apart from each other in order for them to even have a chance of destroying them, you know, any kind of destructive interaction, right? So they're not going to be that far apart. They're going to be very close. Therefore, what will happen is they'll just get louder, but they won't cone filter at those frequencies. They'll just get louder. That's something you can fix with EQ. Right? If all these low frequencies just get louder, but they're staying coherent, then great. I can just put a low shelf, knock that down off the cluster, and I'm back flat again. Okay? And we know that those low frequencies will get louder consistently at all angles, right? Because they're not controlled. So that's okay. So in order to create an array, you're looking for this kind of a beam width, where you want it to be consistent all the way across.
So you're saying you want to do that?
No, I'm not saying that. This is not a line array does not do this. A line array does the exact opposite of this. A line array box goes. It's a diagonal line. It starts really omnidirectional and gets narrower, 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 narrower as you go up. That's what a line array cabinet does. And arraying that is a very, very different beast than arraying a point source thing. And so I do want you to do this with point source clusters. So that's what I taught you to do. So don't try to do this with a line array cabinet, because line arrays work quite a bit differently. So that I would say probably don't try to do that, because that adds a layer of complexity that I'm not sure you would successfully navigate. Okay, so if you can find polar plots for it, so this is the problem: is I don't care what you use, but you have to be plotting data that is real. You can't be making up the data. Okay. So it has to be something that you can get polar plots for, because you need to be. It has to be polar plots, because that's the only one where you can see, you know, incremental changes in level per angle, right? A beam width plot doesn't tell you that. Beam width plot just tells you at what angle it hits 6 dB down. It doesn't tell you at what angle it hits 3 dB down or 2 dB down, and you need to know that. Okay. So yeah, you can do it now. If you want to like totally skew the results, you know, you could say, well, I'm going to purposely do one that I know is not going to work just for fun, and then I'll do one that I think probably work, and then choosing between the two is easy, right? Right.
So when you say that we should present two different options
Yeah.
for Java, that would be like two separate paths of two different.
So you're gonna choose two different loudspeaker clusters, right?
And those clusters are getting to the same loudspeaker.
Or right, I mean, yes, probably. Yes, they should. In your case, they should. They don't have to be, but for the purposes of this exercise, they should. Because it gets hairier when they're not the same. Because then you have to deal with what's called asymmetrical point source arrays, and that's weird. It's possible, but weird. You could read in Bob McCarthy's book about that. So yeah, the point of doing both, guys, is I want you to do two, just so that I can see two different kinds of data, and I know that you actually did the math, right? That.
So you want us to make one that's like not very good, and
No, I want you to do two different options, right? Because I want to see if you can separate the data, right? Because all of the difference in the distance differences will be the same, right? Because even if you're looking at two different loudspeakers, presumably you're hanging them in the same spot, and therefore all the distance values will be the same, but the directivity will be different. So I want to see you traverse that. I want to see if you can find that line between difference in level as a result of distance and difference in level as a result of directivity. Okay? That's why I'm asking you to do both, because you have to understand the difference between those two data points, distance and directivity. They're two different things. Okay. Excellent. So that needs to be done.